Okay. Hi, everybody. Thanks for being here on the nice afternoon on Friday, late night, let's say. My name is Sven Janko, and the reason for having two names here is that Michael Hunger has created this application, which I want to show to you. He just has been on his way back from Austin, Texas, and just arrived at home, and that's why he cannot be here tonight. And that's why he asked me to do that. And it's a favor for me, of course. So what are we talking about tonight? Well, it's all about the recommendation engine with Spring Data Neo4j in version 4. So let's have a quick look at the agenda for tonight. That's Neo4j and Spring Data. So I will talk about Neo4j, what is Neo4j, and I will give some notes on the Spring Data project. And after that, we will see what is our domain model like, and then building upon that model some recommendations with the Cypher query engine. And after that, of course, we will also have some time for questions, if you wish so. Okay, what is Neo4j? Well, actually, Neo4j is a database. And we will see in the next few minutes what it's based on and what it's good for, and compared to a relational database, what are the advantages. So when it comes to relational databases and your objects, you will always run into some, let's say, issues. So that is, on the one hand, the mapping of your connected domain models. So that's the object relational mismatch or impedance mismatch. You will come across that if you use objects in your domain and in your application and storing them in a relational database. And at one time, if you have a lot of data that you store in your relational database and a lot of data that is connected, you will need to join several tables, and that's when your queries run slow. And that's when Neo4j or in general a graph database come in, and that's where they are very fast. And of course, if you change your domain model, you will always need to think about remodeling your model, and your schema changes somehow. And in contrast with a graph database or Neo4j, we have a schema-less model, and if we change our application design, we can easily adjust the data model without having to think about denormalization or things like that. So if we think about requirements that we are faced with usually today, that are, well, I want to scale my application, that's first, of course, and I want to have variable structures, so I want to have flexibility in my data model. That's what I've talked just about with the schema-less approach. And of course, we always want to have connected data. So in fact, there is almost no use case where you have data which is not connected to some other data. So that's a picture of Facebook, and it just shows you that the whole world is actually connected, and that's why we also need a way to store the connected data. So let's see how we can evolve a simple model for using it in a graph database. The first thing we would usually do is to go to the whiteboard and draw some nodes and connections between those nodes. And we will see then that this actually is your physical model. So you can, if you have drawn your nodes and relationships, you can just easily copy-paste it into your, let's say, computer or into your application and using it for querying and exploring your graphs. So that's a very easy way, and it's an efficient way to start building your applications. The next thing we want to look at is the property graph model, which is the basis Neo4j and a graph database in general is working on. So what are the main building blocks for our graph model? That is, on the one hand, the nodes. So in this simple example, we are seeing 3 nodes here. That is 2 persons and 1 car. And as I said before, those nodes, of course, are connected. Those connections between the nodes, we call them relationships. And those are another building block of the property graph model. The nodes we are seeing here are having names on it. So that's person and car in that case. Those names we call label in our property graph model, and they can be used to group a certain amount of nodes together for querying them and for actually reducing the size of your search area. What we also see in the simple example is that nodes can have properties or key value pairs in general. So in that case, Dan has the attributes name, born, and Twitter. And what I mentioned with the schemaless approach is that we do not have to add the same attributes to all other person nodes. So we see here Anne doesn't have the Twitter attribute. In general, a person node can have any attribute that you wish to. So you don't have to stick to the attributes you have once added. So back to the relationships. We are seeing here a relationship has a name on it, and this we call relationship type. So in that case, that's love or lives with. And we're seeing also that a node can have multiple relationships. And we're also seeing that the relationships are directed. A relationship must have a relationship type and can only have one relationship type, and it must be directed. So to sum up this example, relationships can also have properties on it. This is what we are seeing here. We are adding some more information on the relationship. So one information is the relationship type, sorry. And another information we have is, in that case, the date, since when this person drives the car in that example. So once you decided to use a graph database, you need to think about transforming your data which you have in your application so far. So this is when it comes to transforming, for example, relational data to a graph database. And what we typically have for connected data in a graph database is, in that example, for those 2 entities, person and friend, we would have another table which connects those 2 entities. And we would have some foreign keys which we need to look up in order to know which persons are actually connected. And in a graph, this is much simpler because we do not need a separate node or a separate table. We just have our person here, and then we have all the connections to other entities which he is connected with. And when it comes to traversing those information in the model, this is when a graph database is very, very fast. So we don't need to scan the whole table, but we just need to follow along relationships we have. So that's just pointer following pointers we have on the node. So once we have found our entry point to our query, we are very fast traversing through our graph model. So in fact, that's all about patterns. We've seen a node, a relationship, and another node. And we now need some way to transform that into a query. And we use Cypher for this, which is query language in the form of ASCII doc notation. And what we are doing here is we are using brackets to define the nodes, like here. And we are also defining the parameters. In that case, that's name n. And then we are also using the square brackets for the relationship and putting the name behind the colon. So that's what we're seeing here. And then again, the same notation for the other person. So yeah, there's the question, please. Do have nodes primary keys is the question. Yep. The nodes, each node has a key that is called ID. Each node has a internal database ID, let's say, and with that you can identify the nodes. Right. Okay. So what if we now want to know something out of our graph database? So that's we talked about. Okay. So if we now want to know who is Stan in love with, so we would just simply type our same notation here. For the node, we have the same notation for the relationship. And then we are giving an alias to the person we are looking for. So in that case, we still don't know the name, but we are returning it by just returning the alias love. And this is a very simple way of querying your data and finding paths in your database. Okay, as I said, the graph database is very fast when it comes to traversing relationships, and that's why the relationships are your first-class citizens in your database. And I also said that it's very fast when you have your entry point and then traverse your data, and that's when when it's much better than a relational database. So just to name a number here, we can make up to 4 million traversals within a second once you have your entry point. And that I think is huge, because just try that in a relational database. I don't think you will make that with joins and so on. That's almost impossible. And we've just learned, in fact, the first query in Cypher. So Cypher is the query language we are using for querying our data. We will see that later on in much more detail. Okay, let's now talk about Spring Data. Well, Spring Data is, as you might all know, the most active Spring project, and the main goal of Spring Data is to provide a familiar and consistent Spring-based programming model for accessing your data, while still retaining the functionality, the special functionality of your store, of your database. So in that case, this is Neo4j, and we still retain the special functionality of Neo4j, which is traversing and being a high-performance database storage. So let's give you a quick overview of the history of SDN, of Spring Data Neo4j. Well, it all started with SDN 0, which has been written by Rod Johnson and Emil Eifrim. Both of them are still connected to Neo Technology. Rod is, beside others, a board member of Neo4j, and Emil is the CEO. After that, SDN 1 has been released with some new features regarding embedded Neo4j and object mapping and templates. We will see that later if we look into some code examples. And then after that, version 2 supports Neo4j server and also the repositories, which we also see in the code example in a few minutes. And then with Neo4j in version 2 released, we added support for labels and schema indexes, and that's what SDN version 3 deals with mainly. And after that, today available, this is SDN version 4.1.1, and this is what we have used for our example application. We will talk in the next, with the next few slides. I will give you some key features that have been implemented in that version compared to the previous ones. And we are using Spring Boot in version 1.4. This is not an official release so far. That's why we used a snapshot in that case. So if you want to bring your applications in production, you should wait a few days for this version being released. With Spring Boot version 1.4, your application works out of the box. So Spring Boot works out of the box. So let's talk about Spring Data Neo4j. What is new in version 4? In fact, version 4 is a complete rewrite of the version 3 with the main focus on performance and supporting Neo4j server. So at this point, let's quickly talk about the two ways of deploying Neo4j. You can do this in a server environment, so you have a dedicated server layer and then connecting your client applications to that. Or on the other hand, you could do that in an embedded version so that your database runs within your JVM. That's the differentiation between those two, and Spring Data Neo4j focused on using the server variant because that's what most of our clients are using. And we have added support for some transport protocols. Mainly this is Cypher over binary protocol. We have introduced a new binary protocol called Bolt. And we also support HTTP and embedded still, of course. Okay, some more features of SDN 4. That is the Neo4j OGM, which is Object Graph Model. In fact, the main part of the functionality of SDN was shifted to OGM, to the OGM project, so that you also can use OGM as standalone without using Spring. In our example, we of course use Spring, and I would also recommend to do so, but it's possible to use only OGM. The main reason for that was that we are now no longer dependent on the Spring release cycle and can also provide updates faster. And there's been also some work on the metadata scanning. So we're now using no reflection, so we can very quickly scan the data. And we also support variable depth persistence. Variable depth persistence is, well, the depth of your traversals is the number of relationships you go. So let's say you have a node which is connected to another node, and then this node again is connected to another node. So you have two relationships, so the depth would be 2 in that case. And if you don't want to store all the data that is being fetched from the database, you can reduce the depth parameter in your application and then saying just store or just persist the first level. That's all I want to persist. That's what variable depth persistence is managing. And we have also the possibility to define different session scopes. So if you have, for example, a standalone application, you would go for the application context, which then maintains one entire session for the lifetime of your application. Or if you have a web application, you can go for HTTP requests or session scope. And the last feature on that slide is smart object mapping, which means Neo4j and SDN is only storing those information which you have adjusted. So if you have once read your data from the database and then adjusted some properties in your application and then saying save, Neo4j and SDN in fact is knowing which parts of your data have been adjusted and then only sending those information to the database. This brings two advantages. One is you have less communication over wire, and the second is you have less computing time on your server because less data has to be stored. And those points we will see in our example. Spring Data Neo4j, of course, comes with all the Spring templates here, the transaction management, and the repositories, and query support. We'll see that in our code examples. Okay, then, let's talk about the recommendation engine. Well, we will walk through the domain model and then discuss the entities we will extract out of that, and then we will see also some queries for recommendations. Our domain is the meetup.com site, where you can look for some meetup groups to join. And from that, we now want to build our data model. So this is an example of a web page. What we're seeing here is the Neo4j London user group. And those red areas here are the information we are interested in. So on the one hand, this is the events. So there are some events which take place, and this is our first entity. And then there are some people, of course, using the site and looking for events and rating events, for example. This is our second entity. And we also have some topics which are related to groups. And we also have some activities. So when a user joins a group, for example, or when a user is interested in some topics, those are the activities. And what we now know from that is our entities. So this is the groups, the members, which I previously denoted by users, and we have the events, the topics, and what I didn't mention so far is the location. So an event takes place in a location, of course. So these are our entities or our nodes. And then we have the activities, as I said, which then map to our relationships. So that could be a member is joining a group, a member is interested in a topic, or a group is about a topic, and one or two others, like you can see here. So this is actually our domain, our meetup domain model. We have on the one hand our entities, which are our labels, in fact, in the database, and we have our relationships. So let's see how this looks like in a graph model. Well, we have our nodes, an event, a member, topic, and group, and those nodes are then connected via the relationships. Here I'm missing some parts of the relationships. Sorry for that. Oh, it's not coming. Okay, so a member, for example, is a member of a group, that is this path here, and a member is also interested in a topic, and a member also can subscribe to an event. And a group takes place in some event. A group hosts some event, and this event takes place at some venue. And a group, as I said, has some topics, several topics, which they are talking about. So that's our domain model. And on that model, we now think about a use case we want to query, we want to have a recommendation for. So that's a very simple use case we will talk about. That's about similar groups. So the use case is, as a member of a Neo4j meetup group, I want to find similar meetup groups so that I can join these groups. So what we now need to think about is what makes up similar. So in our case, similar is when a group has the same topics, to keep it simple. You could always add some scoring or rating function here for making similar to work for your application. In our case, we just say it's similar when there are the same topics in the same in one group, in two groups, sorry. So we now have our use case or our user story written. The next step then is to draw a graph of that user story. So that's again one part of our data model, in fact. So we've seen that path already, at least the connection between group and topic. And what we're seeing on the right is exactly the same. Again, a group is connected to the topic. So what we now have is we have our group, which is connected to a topic, and then we have some other group or other groups that are also connected to the very same topic. And that's what we are interested in. We're interested in this group here. So the next step then is to write our query. We've seen how we do that already. It's very simple. We're using the nodes annotation and the label and the relationship annotations to transform that into Cypher. And then, when we have transformed that part of our data model into Cypher, we can easily add some keywords and finally get to our finally come to our Cypher recommendation query, to our first simple Cypher recommendation query. So in that case, we're using match, which is a Cypher keyword, which says, give me all the nodes that match that pattern which follows. The pattern we have also seen, we've just evolved. I don't think I need to explain it again, because that's what we've just drawn in the data model. And then we just need to specify which group should be our entry point. And this is what we are doing with the where clause. So in that case, we're saying, give us or look up all groups that contain the name Neo4j in that case. And from that, traverse the graph and find similar groups. And then we are returning, in that case, the name of those other groups. And we also use aggregation functions and return the number of rows, the number of hits in that case, that are in common with the Neo4j group. So, and then we simply order it and say we just want to have 10 of them. So that's then the result. I don't think all of you can read that, but it's not of importance here. The important thing is we're getting some columns which we have defined in our return statement. I'll switch back to the previous slide. So that is 3 columns because we returned a group name and we returned the number of topics in common, and we also returned the topics name as an aggregated array. So, and then that's what we are getting back, and then we can use that for further operation in our application. So the next still simple use case is, as a member of several meetup groups, I want to find other similar meetup groups that I'm not already a member of, so that I can join them. So the difference here is we are now looking at groups that we are not still a member of. So again, we need to define what is similarity in our case, and in that case, we are using the interests. Again, we are drawing the partial graph model. In that case, we are having the same as before. That's the group and the topic connection, and we add the information of the member. So we have the member which is interested in a topic, and we also have the member is also a member of the group. So those two connections have been added here. And with that, we again can write our queries. In fact, it's again copying, pasting it, in fact. So this first one here is the member is interested in the topic, which is this path. And then we have a member which is a member of a group, and that group has a topic. That's this path. And then we have a topic which is part of another group. So that is this path. And then the last thing is we need to define that we are not a member of that group. So that's what we do with the last clause here. And then again, we can transform that or put that into a Cypher query, and then it looks like this. So the first part here we've just discussed, and we've just got out of our partial graph model. And again, we are defining where is our entry point, which is done with the parameter here in that case. So we're saying where the member name is a specific name. You could also use an ID, of course, to specify which user you're looking for. And then we are piping through those results. That's what the with clause is doing. And then we are matching those results and saying, just give us a subset of that result. And that is where the other group has the same topic. And then we are adding the where clause for defining that the member is not a member of that other group we are looking for. And then we are returning the same results as in the previous query. That is the group name and the name, the topic names, and some scoring here in that case. And then again, we get back our results. So I have another use case here, which is a bit more complex, but I'd like to skip that because otherwise we would run out of time. So let's skip that one. Okay. So far, we have seen how to write simple Cypher queries, in our case for recommendation engine. And at this point, just let me mention that we have a whole day covering that topic, whole training day. So if you have specific questions about that, just join me after that. Or if it's too much for explaining in 10 minutes, you can always visit some of our trainings. Okay, then let's talk about the example application. So at that point, we have our queries but we don't have our data yet. So we need to somehow import our data from the Meetup domain. So what we've done here, or what Michael has done, is to use the Meetup API together with the Spring Social project to extract data from the website or from the meetup.com to import it into the Neo4j database. The API is a REST API endpoint with REST endpoint, with REST templates. And as I said, together with the Spring Social project, it's very easy to extract the data and save it in our application as a graph model. So let's see how that looks like in the code. So here on top, we have a Meetup template, which we are using in order to query the data out of the Meetup domain. This is what we are doing with the function findByRadius here. So we are looking at the group operations of the Meetup template, and we are giving a city and saying give us some groups back which are in a given radius of that city. And then we're using the Stream API in order to map them to our groups. So here we are defining the entity, which is our group entity, and then maps to our node, which actually the group node in the database. And then we are collecting it as a list and saying, save us that list into our database. That's where the repository comes into place, and we are just calling the save function and passing the groups list. I hope that is still readable. Can you all read that in the last line? Okay, perfect. So in that example, we are now looking at the again at the Meetup domain, and then we're saying find us some groups by ID, and we are iterating over all those groups we have previously received, and then we're saying find us all events of that group. So in that part of the code, we are creating a venue out of the event, and we are creating the event and saving it. So let's look into a bit more detail here. We are querying again the Meetup template and saying we are interested in event operations, and there find us some groups which we already got from the previous slide. And then we are creating a venue and passing the venue which we get back from our API. And then we are executing some Cypher query here, which is written in green. And there we pass the venue ID, and then we create the domain model, which is in our case the event, and passing that to the save function. That's a very quick and easy way to extract the domain data out of the Meetup domain and save it in our Spring Data Neo4j application. So this is not the only way to import data. You could also use some REST API and use, for example, curl to receive your data and transform that into a CSV file, and then use the import function of Neo4j to transform it into your database. So that's just another example. We don't want to focus on that because we just had a good way of doing that with Spring Data Neo4j. So that's a simple example how your data could look like in the Neo4j browser. If there's some time left at the end, I will show you the browser and can show you some things you can do with that. So now the recommendation engine example, actually. So what does our domain models look like in code? First, let's talk about the application architecture. So we are using a Spring Boot application, as I have said before, and we are defining some REST controllers in order to have clients that can interact with our application. And we also, of course, use the features of the Spring Data Neo4j, which is the repositories, for example, in order to manage our domain objects. So first, the configuration. On the very top, we have the annotation Spring Boot application. And we are also telling that we want to make use of the transaction management. And we also say that we also give the framework the domain package, which we have in our application. So in that case, that's the com.meetup.domain. Then we have the environment, which is being injected by the framework. That's this variable here. And then we are defining a simple Meetup template bean, which can be received in other classes. We have seen that actually when we imported the data from the Meetup domain. So we have just used this Meetup template actually. So now let's talk about the entities. So we had a group node or a group entity, and this simply maps to a class in Java, which is called group, and which is annotated by the node entity annotation. And then, as I have said, each node has an internal database ID. This is why we need to annotate the graph ID to the long ID variable here. And then we are defining all the properties which we had on our node. So a group has a group ID. Well, that's our group ID interpretation. And then it also has a name and, let's say, a slug, for example. And then we need to define which relationships are coming in and going out from that node. And this we are doing by annotating the relationship annotation. In that case, we are adding the information type, which is in fact our relationship type we have talked previously about. So in that case, we have a hosted event as relationship type. And now we know that a group is connected via the relationship type hosted event to some events. So we see that we are using the set type here for our member and saying it's a set of events. And behind the scenes then, SDN is managing this set for us and adding all the events that are connected to that group. And the same is true for members, with the difference that that the direction is the other way around. So that's why we need to define the direction parameter and saying this is incoming. This is an incoming direction. And then again, the group has some topics. There's nothing new compared to the other two examples here. And then we have our member. It's actually the same structure here. There's nothing new compared to the previous example. We have, again, our node entity, graph entity, and the relationship with the relationship types. So the event then also is annotated with the node entity, and it also has some relationships. And again, we are defining the outcoming and incoming directions here. So if you now think about our previous example, we have talked about two very, very simple recommendation examples. You could also, as I've already said, use a complex rating function in order to make your recommendation more sophisticated. And that is an example how you can then model a relationship which has some attributes, some parameters on it. So let's say we have a member which is connected to an event, and this event has been rated with some parameters by the user or by the member. In that case, we are choosing stars and comment. And those two are then our properties that are on the relationship type, on the relationship actually. And the keyword or the annotation name for that is relationship entity. Okay, then I've said that we are making use of repositories to define our queries. And this is an example this is the first example we've talked about. So we've just copied the query we have built previously to the query annotation. And we are defining the type which is being returned. This is a list of topic ratings. And the topic ratings is a special class or a simple class which we define. In our case, it's an inner class. You could also define that as a normal class, as you wish. And in that case, we are returning two information here. This is the topic, which is an object, one of our domain objects, and we are returning a simple integer value. And those two are being mapped by the SDN framework. So in that part here, we are returning a topic, and we are returning the number of rows and defining an alias, which is the alias hit. And that's how the framework knows then that it needs to map those two information to that class. That's one way of defining a repository by annotating it with the repository REST controller annotation. And another way of doing that, of defining a REST controller, is to specify it with the repository REST controller in that case. That's the same, sorry. That's another example of that, a bit more sophisticated, which I was talking about here is defining it by a REST controller, actually. So in that case, we are defining which name to use as the REST endpoints for our functions. And in that case, we could execute arbitrary Java code to do some more application logic here, to implement some more application logic. Okay, let's see how you can get started. I've collected some useful sites for you if you wish to have a look at that. So that's the Neo4j page, of course, where you can download Neo4j. You can also visit the Spring Data Neo4j project page, of course. And you can also find the demo application here, and also some other links to the code of OGM. Okay, so let's see if we have some more. No. Okay. So I think we're just in time. Do you have any questions we want to discuss here in the group? Yeah, go ahead.
Okay, I wanted to ask whether you have some in-memory implementation which you can use for testing purposes.
Well, we have in-memory computing with the Spring Data Neo4j, and you can also test your application using the in-memory database, right? So when you test, you can start up a database in memory and make operations on that. That's true. Yeah.
Okay, thank you.
Okay, then if you want to reach out to me or to my colleague Michael, you can email us or find us on public Slack Neo4j channel. Yeah, so thank you for listening.